how do we represent compounds? Well, we have a shorthand because it just makes things easier. So the compounds have constant composition with respect to their mass because they're composed of atoms in fixed ratios. And so what we call a chemical formula is a representation of the relative number of atoms of each element that are present in that compound. So we use the element symbols and we use subscripts to indicate how many of each there are. By convention, a subscript of 1 is omitted. Scientists, chemists especially, seem to have this aversion to writing the number 1. And you'll see throughout this class, we often don't write the number 1. So common chemical formulas include NaCl. That's the formula for table salt. This indicates that there's 1 sodium atom for every 1 chlorine atom in the molecule. We don't write the ones. The way I think of it is, if there weren't any, I don't write the symbol. So the fact that I wrote the symbol tells you there's 1. If there was more than 1, I would write a number to tell you how many. So writing the symbol indicates that there's 1 of them. CO2. There's 1 carbon and 2 oxygens. This subscript 2 tells us there's 2 oxygens. Here's the formula for table sugar, sucrose. C12H22O11. There are 12 carbon atoms for every 11 hydrogen atoms. That's not an 11, that's a 22. 12 carbon atoms, 22 hydrogen atoms, 11 oxygen atoms in each molecule of sucrose. Those subscripts are important. They're part of the description. If you change that, you change the compound. So here's an example. We have carbon monoxide and carbon dioxide. Their formulas are very similar. CO and CO2. The 2 is really important. Carbon monoxide is a dangerous gas. It's poisonous because it will displace the oxygen in your blood and cause you to suffocate, basically. And sadly, I think just last week there were 2 people in Fresno who died in their home of carbon monoxide poisoning. If you have a gas appliance that's not properly vented, it can build up in your house and kill you. My own family, when I was a kid, we had a close call at a cabin with carbon monoxide. Carbon dioxide, the only difference is it's got 2 oxygens instead of 1. Carbon dioxide is not toxic. It's present in the air. When we breathe in oxygen, we breathe out carbon dioxide. Very different properties, poisonous versus not poisonous, right? The difference is 1 oxygen atom. So this is one of those cases where details matter. Sometimes details really matter. You're sending a very important letter to someone by email, and you type one of the letters in the email address wrong. Is it going to get there? No. You put 1 wrong number in a chemical formula, it's a very different compound and has very different properties. We do have a particular order in which we list the elements, and this is not going to be a big deal in this class, but I just want to let you know what the reasoning behind that is. We generally list the most metallic elements first. And remember, we learned to look at the periodic table, and the metals are on the left, and the nonmetals are on the upper right. And so you can look at the periodic table and identify which one is more metallic. So we write NaCl instead of ClNa. This looks like baby talk to a chemist. It's like, well, I know what you mean, but that's a very backwards way of saying it. When my second son was about 2, we were at a restaurant, and he was going on and on about the dollar biller. And finally he was pointing, and we figured out he was talking about the cash register, right? The dollar biller. So this is like calling a cash register a dollar biller. That's not the proper name. If we look in the periodic table, sodium's on the left, it's in the metals. Chlorine is on the far right, it's a nonmetal. Another way to help you remember that is we generally read left to right. And so whichever element is more on the left side comes first, and then on the right side. N2O is the correct formula, not ON2. This gives the same ratio, but the order is backwards. If we find nitrogen and oxygen on the periodic table, they are both nonmetals. But which one is to the left? The nitrogen. So we would list the nitrogen first and then the oxygen. There are exceptions to this, but this is the general rule. This is a list from your book showing you the order of listing for the nonmetal elements. That can mostly be figured out by looking at the periodic table and seeing which one is closer to the metal section. There are a few historical exceptions. Sometimes things, were discovered and people got used to them, and then when things got more standardized, everybody was so used to them that nobody wanted to change. And hydroxide is one of those examples. Hydroxide ion, we always write the O first and then the H. And the reason is because we've always done it that way. I know that's not a real satisfying answer, but that's what it is. So let's write a couple chemical formulas. A compound containing 2 silver atoms for every sulfur atom. What would the formula for that be? You have to know your element symbols. What's the symbol for silver? Ag. So this is Ag, and how many do we have? 2. And then the other one is sulfur there's 1 sulfur. What's the symbol for sulfur? S. Okay, so Ag2S. Ag comes first because silver's a metal, sulfur's a nonmetal. Compound containing 2 nitrogen atoms to every oxygen atom. What's the symbol for nitrogen? Capital N. And there's 2 of them, so subscript 2. And then oxygen is O. There's only 1, but I'm not going to write the 1. So N2O. Nitrogen comes first because it's to the left of oxygen. 2 iron atoms for every 3 oxygen atoms. What's the symbol for iron? Fe. So this is Fe2, and oxygen is O3. You need to memorize the element symbols, okay? The ones, there's a table in the book that lists them, and those are the ones you need to memorize. Now, there's, what if you don't remember? You don't have to remember, it's not the whole periodic table. It's just, there's one, hang on. Okay, I can't find that table. I will post the list for you on OneDrive, okay? There's a list, I think it's about 35 that you need to know for this class. If you're, especially like on an exam and you're stumped, you don't remember what the element symbol is, oftentimes a good guess will be the first letter of the name or the first 2 letters. Here's a tip. If it's not on the periodic table, it's not going to be correct, okay, right? Sometimes people want to put, all kinds of interesting things.
IR for iron.
Well, the thing about IR for iron is that there is a compound iridium, an element iridium that does have the symbol IR. So that's going to give you a problem. I can't think of an example right now, but people sometimes come up with something that is not, well, like X for xenon. There is no element X. There's Xe, but there's no just plain X, because that would be confusing. That would look like a variable or something. So if it's not on the periodic table, it's not going to be correct. Some formulas have groups of atoms that act as a unit. And when we have 2 or more of these, then we need to set them off in parentheses. These are called polyatomic ions. So polyatomic ions are groups of atoms that have a charge associated with them. So we learned about ions, right? An ion is an atom that has gained or lost electrons and has a charge. You can also have a group of atoms that together have a charge and act as a unit. So here's an example. This formula, Mg, and then in parentheses, NO3, 2. Inside the parentheses, this is a polyatomic ion. And so we put parentheses around it to indicate that there's more than one of them, there's two. If we had just one of them, we wouldn't need the parentheses. So if we had like sodium nitrate, we'd be okay. But magnesium nitrate, if we don't put the parentheses and we just put the 2 here, it looks like there's 32 oxygens and 1 nitrogen. And that's not what we meant. We meant that we had 2 groups of NO3. So this is a little bit like when you're shopping at Costco. It's hard to buy one of anything at Costco, right? You want ketchup, you're getting 2 bottles, right? You want bread, you're getting 2 loaves of bread. You want a Wii, and you don't want the extra games and controllers, too bad. It's bundled together, right? There's literally shrink wrap around it. These parentheses are the shrink wrap, okay? This is a bundle pack. Nitrogen and 3 oxygens come together in a package. You can have 1 package, you can have 2 packages, but you can't just get the nitrogen and 1 oxygen at Costco, okay? So when we just have one of those bundle units, we're okay. But if we have more than one, we have to put parentheses around it and put the number on the outside. So if we have 2 of these bundle packs, how many nitrogen atoms are there? 2. How many oxygen atoms? 6. So it's a little bit like distributing in math. This on the outside multiplies everything on the inside. Or you can think of it as this is like a tricycle. It has 1 seat and 3 wheels, and this on the outside is saying, I have 2 tricycles. How many wheels do I have? Well, there's going to be 6. 6 wheels, 2 seats on 2 tricycles. Okay, so very important to get a grasp of what this parenthesis business means. So this figure is showing us, here we've got the symbol for magnesium with no subscript. So there's 1 of those. This is the NO3 group, and the 2 on the outside. Okay, any questions? We're getting into a section where, when I explain it in class, it's probably going to be a little fuzzy and you'll be a little unsure. And then when we do problems and do worksheets and we practice it, it'll begin to make sense. It's a little bit like learning to play a new board game. And I can read you the rules for Stratego or whatever you want to play, and it doesn't really make sense until you start playing. Determine the number of each kind of atom in the following formulas. So here's K2SO4. They're asking us to list the different elements. We've got potassium, sulfur, and oxygen. How many potassium atoms? 2. How many sulfur?
1.
And how many oxygen? 4. How about in this next one? Al2SO43. That's how you would read it. Instead of reading this as 40, where's my pointer? 43, I'd read this 4, 3, and then I understand that the 3 was on the outside of the parentheses. We've got aluminum and sulfur and oxygen. How many aluminum atoms?
2.
How many sulfur atoms? 3. And how many oxygen atoms? 12. Because this is a bundle. And with every sulfur, you get 4 oxygens in the bundle. We've got 3 of the bundles. So those are chemical formulas. We have different types of chemical formulas: empirical, molecular, and structural. Empirical is a word meaning from experiment. An empirical formula is obtained by an actual experiment where you perhaps decompose a compound into its elements and measure their masses and figure it out that way. An empirical formula gives relative number of atoms. The molecular formula is what we think of more as a regular chemical formula. Gives us the actual number of atoms that are in a unit molecule of that compound. The structural formula is going to help us to understand how they are connected. In the molecular formula, let's make an example here. So HO might be an empirical formula. That's the empirical formula for hydrogen peroxide. It gives us the ratio, 1 hydrogen for every 1 oxygen. The molecular formula for hydrogen peroxide, though, is H2O2. In a molecule, there's actually 2 hydrogens and 2 oxygens. This just gives us the relative numbers. This gives us the actual numbers. Then a structural formula tells us how they are connected. And you can have multiple compounds with the same molecular formula, but the atoms are connected differently. Just like you could take Lego blocks and put them together in different ways. Now, not all things are possible with atoms, but there are many compounds that have the same number of atoms of each element, the same molecular formula, but the compounds are different. So the structural formula just gives us a little more information. Molecular formula is what we'll use most of the time. We also use models to help us visualize what's going on here. Common one is a ball and stick model, and we represent the atoms as balls and the chemical bonds as sticks. These are like chemists' tinker toys. This is not standard, but in many model sets, we use colors to represent the different elements, so we don't have to have labels on the balls. And so these are colors that are typically used. A space-filling model is going to look more like the actual molecule looks. So the atoms will look like they're kind of going into each other. This is useful for some things. The ball and stick model is useful for others. So here we have a molecular formula, just the letters and subscripts to indicate how many of each. Here we have a structural formula showing how those atoms are connected. These are generally 2-dimensional. You write them on a piece of paper or on a screen. They're flat. But the actual molecule is 3-dimensional. And so this is the ball and stick. We can see quite clearly the geometry of it and how things are connected. But the actual molecule would look more like this. So this gives us a better feel for the real shape, but it's a little harder to look at, especially when you get a really big molecule, because the stuff on the inside gets kind of hidden. So those are different types of models, ways of representing molecules.